So we have examples where we add electric fields together from multiple charges, and we find that there's a total electric field there. But if electric fields can point in different directions and we can have them opposing each other, is it possible to have an electric field be zero despite there being electric fields present? So let's take a look at another example here. We have this example on canceling electric fields. Two charged particles with charges of Q and 2Q. So all we're saying here is that there is a charge, which we do not know the charge of, and another charge which is twice the amount of charge. Those charges are separated by a distance of 10 millimeters. At what distance from the smaller charge does the net electric field equal zero? So we can set up here. So a little coordinate system, positive x to the right. It doesn't matter which way you draw it. In this case, I will just choose to draw the smaller charge on the left and call that one. So let's call it Q1. And let's say it has Q. And we have a bigger charge here, Q2, and it has 2Q. So we need to find the distance or the location at which the electric fields cancel. So specifically, we want the distance from the smaller charge. First, we need to analyze this conceptually. So we need to figure out where are the electric fields going to cancel. So in this case, it's as simple as, okay, if electric fields point away from positive charges in every single direction, we should kind of have a fair guess that somewhere maybe in the middle, our electric fields should cancel. And that would be a good guess in this case, because at this point, which again has nothing there, the electric field would point away from this positive charge Q1, and we would have this line that connects it to this point, so we would draw along this line and away from Q1, which is to the right. So we call that E1. We then have the same thing happening for Q2, in which the electric field will go along this line away to the left, because it's again another positive charge, so it also has electric fields going away from it. So that's a fair guess. We have the electric fields are pointing in opposite directions and they have a chance to cancel out. So in order for these two to cancel out, we would need to have that they point in the opposite direction, so that's the first thing, but we also need to have that they're the same size or magnitude. So in other words, the value of E1 needs to be the same size as the value of E2. So you could say that you could just jump to saying that E1 equals E2. You could add the two up and set it equal to 0, but then you just ultimately get that E1 equals E2. We can use this to then write out what E1 and E2 equals. So KQ1 over R1 squared equals KQ2 over R2 squared. Okay. Now, we would just need to do a little bit of manipulation with this to solve this out. But assuming this works out, let's get a fair estimate of where our answer lies. In other words, is this point going to be exactly halfway between the two, or is it going to be somewhere else between the two? So the thing is that this problem is not symmetrical. You would kind of expect that if the charges were exactly identical, then the balancing point would be in the middle. But there's more charge on this one. So what effect does that have on it? So what would happen is if you were in the middle, then the electric fields would not be equal anymore because there would be more charge from this one on the right. So the electric field will be stronger from charge 2 in the middle. So if E2 would be larger than E1, directly halfway between the two, in order to make it not be the larger one, you would have to go further away from it to weaken its electric field. So we would expect that the balancing point between the two would be closer to the smaller charge. And in this kind of problem, the answer is always closer to that smaller charge. Okay? So let's say that answer, if the distance between the two is 10 millimeters in this problem, we should expect an answer that's less than 5 away from that other charge. Let's say somewhere between like 3 and 4. So let's continue. Now we can clean this up a little bit. So first of all, K cancels out like that. Q1 and Q2 have, well, not numerical values, but we know what they are. It's Q and 2Q. So we can write this as Q over R1 squared equal to 2Q over R2 squared. So we substitute in the values of Q1 and Q2. Now, what do we solve for exactly? So we have a distance R1, which is the distance from charge 1, and we have the distance from charge 2. So what do we solve for? Well, we want to solve for the distance from charge 1 because that's what we want from the problem. It says to find the distance from the smaller charge, which is in this case charge 1 that I've drawn. So I want to solve for charge 1, but the problem is, well, how would I know what R2 is, the distance from charge 2? What we need to do is we need to realize that R2 is directly related to R1 because we know the distance between the two, which is just call it L. The distance from charge 1 is R1 to that point of interest in the middle, and the remaining distance is R2. So there is a relationship between R1 and R2. So if I were to get rid of R2, I would just need to find a way to write it in terms of R1. I could do that really easily if I just realized that the distance R1 plus the distance R2 equals the total distance, call it L. So we use that R1 plus R2 equals the total distance L. So we move it around and say that R2 is L minus R1. We use this, plug it into R2. So we have that it's Q over R1 squared equals 2Q over, and we substitute L minus R1, and then it's squared. Okay. So now we don't have to deal with the issue of having another unknown, R2. We now only have R1. It appears in two places, but it's just one variable. And L is a known value, which is 10 millimeters in the problem. So our goal is to now just solve for R1. There's different ways you could do it, but the way I would recommend to not do it is to not square those out because it just makes it messier. So what we can do is we can collect the terms with R1 on either side. So let's put the R1s on the left side and let's put the Q's on the other side. Now, actually before that, we could also realize that the Q's also cancel because they appear on both sides of the equation and it's just being multiplied or divided to everything. So we don't even have the Q anymore. So if we move this term in the denominator over to the numerator on the left side, we have L minus R1 quantity squared divided by R1 squared equals, and we only have 2 left on that side. Now, this is really easy to just, for instance, take the square root of the left side to get rid of our square problem, which is why you don't want to square it out. So if we square root it, it's L minus R1 over R1 equal to the square root of 2. So this is much easier now. So all we're going to do is we're going to move the R1 back over and we'll collect the terms with R1. So we move this over to here. So we have L minus R1 equals root 2 R1. We add the R1 over, so it's L equals root 2 R1 plus R1. We have 2 terms with a common R1, so we factor it. So we have square root of 2 plus 1. We pull that out and we have nothing left here except a 1 times R1. And we just move that over and we get our answer. So therefore, R1 equals L over square root of 2 plus 1. Now, just by already looking at this without plugging any numbers in, you can already see that you're taking the 10 millimeter distance, which is the whole distance, 100% of it, and you're dividing it by a number which is larger than 1, because this is, square root of 2 is about 1.4, and plus 1 makes it about 2.4. When you do 10 divided by that number, it's going to make it smaller. In fact, it's smaller than 5. So we know that our answer is already going to be closer to the smaller charge than it is to the bigger charge. Plug in the values. We get 10 millimeters. We can leave it in millimeters because it's the only thing with a unit. Plus, and this is approximately 2.41. Okay. So if we do that, 10 over 2.41, we get, let's see, 4.15 millimeters. Okay. So indeed, the halfway point is at 5 millimeters, and the balancing point, which the two electric fields cancel, is closer to the smaller charge than it is to the bigger charge.